Imagine standing in front of an ordinary mirror in a clothing store fitting room, trying on different outfits, when suddenly you see in your reflection a completely different garment, the one you already removed and set aside moments ago, even though your body is currently wearing an entirely different piece of clothing, and this false reflection persists for several seconds before it jerks violently and synchronizes with reality. Or picture yourself picking up an old mobile phone that has been sitting unused for years, pressing the power button, and watching the screen light up as the system begins to load, only to open the back cover and discover that there is no battery inside at all, with the device's only battery lying separately, swollen and unusable, while a repair technician confirms that without a power source, the phone cannot function even for a single second. People across the globe encounter these moments when the familiar laws of physics seem to temporarily cease functioning, when physical objects vanish from reality without any logical explanation, when space behaves as though its geometry has been programmed and a bug has occurred in that program, and when mirrors show something other than what optical laws dictate they should display. Science labels these phenomena as perceptual anomalies or hallucinations. Religious individuals see mystical signs within them, but an increasing number of physicists are beginning to ask themselves a disturbing question. What if these are genuine errors in the base code of our reality that become visible when the system malfunctions? If we hypothesize that our world constitutes an extraordinarily sophisticated computer simulation created by a civilization far more technologically advanced than we can possibly conceive, then it stands to reason that within such a system, glitches should periodically occur that can be noticed and documented, much like how video games sometimes experience bugs, where textures fail to load properly, objects clip through surfaces, or physics behaves incorrectly. Quantum mechanics has already provided us with a comprehensive array of compelling evidence demonstrating that reality at the fundamental level behaves in ways that are profoundly strange and counterintuitive from the perspective of classical physics. Elementary particles exist in states of superposition, occupying multiple locations simultaneously until we perform a measurement. Information transfers instantaneously between entangled particles across any distance in violation of locality principles, and the famous double-slit experiment demonstrates that the very act of observation fundamentally alters the behavior of matter. All of this compels us to reconsider whether our reality might be not the objective and stable substance we have assumed it to be, since Newton's time, but rather a dynamic computational system that responds to observation and optimizes its resources in ways analogous to how modern computer programs operate. The first category of inexplicable anomalies we will examine concerns physical objects that disappear or materialize without any possibility of rational explanation, as though the base code of reality temporarily loses information about where a specific item should be located and cannot recover that data. A person prepares tea late in the evening, places a tea bag into a mug, adds sugar, notices that 2 tea bags remain in the box, then steps into another room for several seconds, and in this moment feels intense weakness, darkness creeping into their vision, a sense that consciousness is about to slip away, but within a couple of heartbeats the condition abruptly normalizes, and the weakness vanishes as suddenly as it appeared. When they return to the kitchen to turn off the boiling kettle, they discover that the tea bag they definitively placed in the mug 60 seconds earlier has vanished without a trace existing, neither in the mug, nor on the counter, nor anywhere else within reach, while the box still contains the same 2 tea bags that were there initially, as though the 3rd tea bag never existed in this version of reality. This is not a matter of forgetfulness or inattention, because the sequence of actions was simple and clear, occupying no more than 1 minute of time. No other person was present in the apartment. There were no pets that could have carried the tea bag away, and no physical process can explain the complete disappearance of an object from the enclosed space of a kitchen. From the perspective of quantum mechanics, there exists a concept called the wave function, which mathematically describes the probabilistic state of a particle or system prior to measurement. And when observation occurs, This wave function instantaneously collapses into one specific state from among countless possibilities. What if something analogous occurs in the macroscopic world, and certain objects temporarily exist in states of uncertainty, especially when no observer is actively perceiving them? This would explain why objects disappear precisely during those moments when a person is not looking at them directly, as though the system is attempting to optimize resources and refusing to render those elements of reality that are not currently within an observer's field of vision. In computer games, developers employ a technique called occlusion culling, where elements of the world are generated only when the player is nearby, and when the player moves away, these elements can be removed from memory to optimize performance, and perhaps something fundamentally similar occurs within our reality as well. Another manifestation of this phenomenon involves neighbors at a countryside property who suddenly cease to exist, not only in physical reality, but also in the memories of everyone except one individual. This person retains clear recollections that in 2010, a family lived on the adjacent plot. They socialized with these neighbors regularly, and there was a boy his age with whom he frequently played. But when he traveled to that location years later, he discovered that where the neighbor's house once stood, there is not even a foundation remaining, and instead there are trees growing that appear definitively older than 15 years. This person's parents do not remember any neighbors whatsoever and assert that nobody ever lived there, despite his possessing vivid memories of shared games, mutual visits, and conversations with this family. If we examine this through the lens of simulation theory, we might hypothesize that an update occurred in reality's database, during which certain elements were deleted from the common timeline, but one individual somehow retained memory of the previous version, perhaps due to a synchronization error during the consciousness transfer process. The phone that powers on without a battery represents an even more flagrant violation of physical laws, because an electronic device simply cannot function without a power source, not even momentarily. When someone retrieved an old button phone, pressed the power button, and observed the screen illuminate as the system loading sequence initiated, they dismissed it as residual charge remaining in the device, but upon removing the back cover, they found no battery installed whatsoever. The device's sole battery lay separately in the same drawer, visibly swollen and clearly unusable, and a phone repair specialist confirmed that without a battery, the device cannot activate even for an instant, because there are no capacitors inside capable of storing charge for years. Yet, for several seconds, the system functioned as though the simulation briefly forgot that phones require power sources to operate, then abruptly corrected the error and shut down. What unifies all these incidents is a common characteristic. Objects behave as though their existence depends not on physical laws but on some underlying code that occasionally malfunctions and creates contradictions. The simulation forgets that phones should not work without batteries and momentarily activates one, then corrects the mistake. Neighbors exist in one version of reality but are deleted from another. Teabags vanish as though the system lost information about their location and failed to restore the data. These patterns suggest that reality might not be the continuous objective phenomenon we assume, but rather a computational construct that processes information selectively and occasionally exposes its digital nature through errors. The second category of glitches involves spatial distortions, where the geometry of the surrounding environment suddenly changes or mirrors reflect something other than what optical laws dictate. A woman exits her doctor's office in a medical clinic and begins walking the familiar route toward the exit, distracted by messaging on her phone, and automatically turns a corner, then turns again, and abruptly finds herself in a corridor that appears as a mirror image of where she should be. The numbers on office doors are written backwards, text is reversed, and at the corridor's end appears an impenetrable darkness that definitely was not there before. And in this moment, such overwhelming fear seizes her that she runs back and collides with a man at the turn. The strangest aspect of this situation is not merely that she entered a mirrored corridor, but that to reach it, she had to turn left twice in a location where physically only one turn is possible, because beyond that point there is a wall. When she returned to the clinic a week later with her husband to investigate the third floor, They searched the entire building thoroughly and found no additional corridor or turn that would have allowed her to access that strange space, as though that location existed only for a brief interval of time before disappearing from reality entirely. Another case involves a mirror in a clothing store fitting room that showed a woman completely different clothing than what she was actually wearing. She stood before the mirror in a sweater she had just put on, but the reflection displayed a blouse she had tried on 1 minute earlier, and already removed, and this reflection persisted for several seconds before jerking abruptly and synchronizing with reality. The physics of reflections operates quite simply. Mirrors show what stands before them. At the present moment, light waves bounce off the surface and form an image. No delays or distortions should be possible. Yet in this instance, the mirror displayed a past state as though it failed to update the image in real time. If our reality genuinely constitutes a simulation, then the developers of this system must constantly render the surrounding space depending on observers' positions. And mirrors present a particular computational challenge because they create recursive reflections of reality within reality. In computer games, mirrors often operate with lag or display simplified images because rendering precise reflections demands additional computational resources. And perhaps something fundamentally similar occurs in our simulation, especially when the system is overloaded or a bug occurs in the code. Yet another spatial anomaly involves a tree's shadow that suddenly vanished for several seconds before reappearing, and remarkably, only one person among 5 standing nearby witnessed this event. A student stood beneath a tree in a park seeking shade from the sun, and literally observed the shadow disappear, not shift to the side due to the sun's movement, but genuinely vanish as though the light source suddenly began shining through the tree, and then the system corrected the error and the shadow returned. The following day, a different classmate who was not even present in the park and with whom he barely communicated suddenly began explaining to him about some half-shadow effect and insisting that sometimes light rays can bypass an object, though nobody had raised this topic in conversation. This behavior appears highly suspicious from the simulation theory perspective, because it creates the impression that the system attempted to explain the anomaly through a non-player character in order to convince the observer that nothing strange had occurred. In video games, developers sometimes program NPCs to provide players with hints or explanations for certain events, and if our reality is indeed simulated, such bots might exist among people, their function being to maintain the illusion of normalcy and explain any glitches through rational causes even when those explanations lack scientific validity. The third category relates to synchronicities and repeating numbers that occur with frequency too high to explain through mere coincidence or selective attention. An individual begins seeing identical digits on clocks multiple times daily. 10, 10, 11, 11, 13, 13, 15, 15. And as time progresses, these patterns appear with increasing regularity, reaching a point where out of 8 instances when they check the time, 5 display mirrored or repeating numbers. Statistically, the probability of seeing identical digits on a clock amounts to approximately 1/24 of all possible time combinations. But when this occurs 5 times out of 8, the probability drops to a level that cannot be explained by randomness. What is particularly intriguing is that these synchronicities began immediately following a strange episode when the person felt intense weakness, darkness encroaching on their vision, believing they would lose consciousness, but within seconds felt dramatically better, while the tea bag they had placed in a mug disappeared without trace. Following this event, they began noticing not only repeating numbers but other changes as well. The shade of wallpaper in their room shifted. Half-a-tone fatigue completely vanished, and shortly afterward they left a job they detested and found new employment with salary doubled. This creates the impression that in that moment a transition occurred between different versions of reality or timelines, and the repeating numbers serve as markers indicating that the person exists in an altered state of consciousness or a different simulation. From an information theory perspective, numbers represent the most fundamental method of encoding data, and if our reality genuinely constitutes a computational system, then numerical patterns might be elements of base code that occasionally become visible to observers. Programmers frequently use repeating numbers as temporal markers or debugging codes that help track a program's state, and perhaps when someone sees 1111 or 1313 with excessive frequency, this constitutes a form of debugging information seeping through the simulation is interface and becoming noticeable at the level of our time perception. Quantum mechanics demonstrates that the act of observation influences a system's state, and possibly when a person begins noticing these patterns, they unconsciously amplify their manifestation through focused attention. In the double-slit experiment, a particle behaves as a wave when unobserved and as a particle when observed, proving the fundamental role of the observer in shaping reality. Applying this principle to the macroscopic world, we might hypothesize that when someone begins paying attention to specific patterns such as repeating numbers, their observation increases the probability of these patterns appearing, creating a feedback loop between observer and simulation. All these categories of anomalies, vanishing objects, spatial distortions, and numerical synchronicities, share one common property. They demonstrate that reality is not the stable and objective entity we habitually assume, but rather a dynamic system that responds to observation, permits errors, and occasionally reveals its computational nature. Quantum mechanics has already shown us that at the fundamental level, matter behaves probabilistically rather than deterministically. Particles exist in multiple states simultaneously until measurement occurs, and spacetime might not be continuous but discrete, composed of smallest units similar to pixels on a screen. But if these glitches genuinely constitute proof that we inhabit a simulation, then a crucial question emerges. Who created this system? For what purpose? And most importantly, can we use knowledge of its existence to understand the deeper laws governing our world? Part 2 will reveal the scientific foundations of simulation theory, explain why physicists are taking this hypothesis increasingly seriously, and demonstrate what experiments are already being conducted to test whether our reality is a computational construct. 3 categories of reality glitches, vanishing objects, spatial distortions, and numerical synchronicities, demonstrate that our world behaves less like stable matter and more like a computational system that optimizes resources, responds to observation, and occasionally exposes its underlying code through errors. Quantum mechanics already proved that reality at fundamental scales operates in ways incompatible with classical physics. Particles exist in superposition until measured information transfers instantaneously through quantum entanglement. Regardless of distance, and observation itself determines whether matter behaves as wave or particle. These aren't merely interesting theoretical curiosities, but empirical facts confirmed through thousands of experiments, and they suggest something profound about the nature of existence that most people prefer not to contemplate because the implications prove profoundly unsettling. The concept of wave function collapse provides the most compelling bridge between quantum weirdness and simulation theory. Before measurement occurs, a particle exists mathematically as a probability cloud spanning all possible states simultaneously. But the moment observation happens, this cloud instantaneously collapses into one specific outcome. From a classical physics perspective, this makes no sense. Why should the universe care whether we're looking? But from a computational perspective, it's perfectly logical. Why waste processing power calculating the precise state of every particle in the universe when you can store them as probability distributions and compute specific values only when an observer requires that information? Video games employ identical logic through a technique called frustum culling, where the engine renders only what appears within the player's field of view, leaving everything outside that cone unprocessed to conserve computational resources. If our reality functions similarly, then objects should exist in lower-resolution probability states when unobserved, and snap into high-resolution deterministic states only when measured, which is exactly what quantum mechanics demonstrates happens. Quantum entanglement presents an even starker challenge to conventional physics while aligning perfectly with simulation logic. When two particles become entangled, measuring one instantly determines the state of the other regardless of the distance separating them, apparently violating Einstein's cosmic speed limit on information transfer. Physicists verified this through Bell test experiments that definitively ruled out the possibility of hidden variables, proving that the correlation between entangled particles is genuinely instantaneous rather than predetermined. From a physics standpoint within spacetime, this appears impossible, but from a database standpoint, it's trivial. If two particles represent linked variables in the same data structure, updating one automatically updates the other because they're not actually separated by physical distance at the code level. The appearance of spatial separation exists only within the simulated environment itself, while the underlying variables occupy the same memory space. Philosopher Nick Bostrom formulated the simulation argument in 2003, establishing that at least one of three propositions must be true. Either civilizations destroy themselves before achieving the technology to create consciousness simulations, or advanced civilizations universally choose not to create such simulations despite possessing the capability, or we almost certainly inhabit a simulation. The logic is straightforward. If even one civilization in the entire history of the universe develops the ability to run ancestor simulations containing conscious beings, they will likely run not just one but millions or billions of such simulations, and each simulated civilization might eventually run its own nested simulations, creating a vast hierarchy where simulated realities outnumber base reality by orders of magnitude. Statistically, if simulated universes vastly outnumber the original universe, the probability that we occupy base reality rather than one of countless simulations approaches zero. Some critics argue that consciousness cannot be simulated, but this objection merely pushes the question back one level. If consciousness requires something beyond computation, then either simulations remain impossible, or our consciousness already operates on that non-computational substrate, making us potential simulations regardless. The fine-tuning problem in physics provides additional circumstantial evidence. The fundamental constants governing our universe, gravitational constant, electromagnetic coupling strength, cosmological constant, mass ratios between elementary particles, all fall within extraordinarily narrow ranges that permit the existence of stable atoms, stars, planets, and ultimately life. The cosmological constant proves particularly striking. Theoretical calculations suggest it should be 120 orders of magnitude larger than observed. Yet it possesses a value so precisely calibrated that deviation by even one part in 10 or 120 would either collapse the universe immediately or cause such rapid expansion that matter could never coalesce. Multiple independent constants display similar fine-tuning, and while the anthropic principle offers one explanation, we observe these values because only universes with such values produce observers. Simulation theory provides another. These constants were deliberately configured by the programmers to enable the emergence of complexity and consciousness within their simulation. Planck length and Planck time suggest that spacetime itself may be quantized rather than continuous, consisting of discrete units analogous to pixels on a screen. The Planck length represents approximately 1.6 × 10⁻⁵ meters, below which the concept of distance becomes physically meaningless according to quantum gravity theories, while Planck time equals roughly 5.4 × 10⁻⁴ seconds, representing the shortest meaningful time interval. This implies that reality possesses minimum resolution limits in both space and time, exactly what we would expect if the universe runs on finite computational resources. Calculating infinitely small distances and infinitely brief durations would require infinite processing power, but a simulated universe with discrete spacetime units needs only finite computation per frame, making the entire cosmos computationally feasible even for advanced but non-infinite civilizations. Some physicists propose experimental approaches to detect simulation signatures, Professor Thomas Campbell suggested an experiment based on the hypothesis that simulations optimize computational load by rendering observed regions in higher fidelity than unobserved regions, similar to video game level of detail systems. The experiment would measure whether particles behave statistically differently depending on whether they are observed in real time versus data collected for later analysis, with any detectable difference potentially indicating that the simulation allocates fewer resources to delayed measurements. While technically challenging, such experiments could theoretically distinguish between a universe that processes everything equally and one that prioritizes currently observed phenomena. Researchers also examine cosmic ray anomalies for computation limits. Particles with energies exceeding the Greisen-Zatsepin-Kuzmin limit arrive at Earth despite theoretical predictions that they should have lost energy through interactions with cosmic microwave background radiation long before reaching us. And if accurately simulating such ultra-high energy particles demands excessive computational resources, the system might employ approximations that create detectable anomalies in their behavior or distribution patterns. Current data shows some unexplained features in the cosmic ray spectrum, though whether these stem from simulation constraints or merely incomplete physics remains ambiguous. Physicist Melvin Vopson proposed testing the second law of infodynamics, which postulates that information entropy in closed systems tends toward minimum rather than maximum, contrary to thermodynamic entropy. If the universe constitutes an information processing system, it should display optimization patterns consistent with efficient computation, and Vopson suggests examining whether elementary particles minimize their information content in ways that would make sense for a computational system attempting to conserve resources. Experimental verification would involve precise measurements of particle states over time to detect whether they evolve toward informational simplicity more aggressively than pure physics would predict. The philosophical implications prove as significant as the scientific ones. If we inhabit a simulation, questions about consciousness become more acute. Are we genuinely conscious beings, or merely algorithms generating the illusion of subjective experience? Philosopher David Chalmers argues that computational substrate does not matter. If a system processes information in ways that generate qualia, it possesses consciousness regardless of whether that processing occurs in biological neurons or silicon transistors. This suggests that simulated beings can be authentically conscious even while existing entirely within a programmed environment, making their experiences, emotions, and moral status equivalent to those of beings in base reality. Free will becomes even more paradoxical within simulation frameworks. If every decision results from deterministic code execution, then genuine choice appears illusory. Yet if the simulation incorporates quantum randomness as an unpredictability source, our decisions might be indeterminate without necessarily being free in any meaningful sense. Alternatively, the simulation might exist specifically to study how conscious agents behave when granted genuine decision-making autonomy, in which case free will could be real within the simulation's parameters even though the entire experiment was designed externally. The question may be fundamentally unanswerable from inside the system, similar to how Gödel's incompleteness theorem demonstrates that sufficiently complex formal systems cannot prove their own consistency using only their internal axioms. Meaning and purpose undergo radical reinterpretation if reality is programmed. We might exist for specific purposes intended by simulation architects, or we might constitute unintended emergent phenomena arising from complex system dynamics. Some philosophers argue that discovering we're simulated should not diminish life's meaning, because significance emerges from internal relationships and experiences rather than external validation, while others contend that being experiments in someone else's research project fundamentally alters how we should understand our existence. The possibility that simulation architects might communicate with us or intervene in our world opens entirely new dimensions of inquiry analogous to theology, but grounded in computational rather than supernatural frameworks. The accumulation of anomalous evidence, from quantum mechanical paradoxes to personal experiences of reality glitches, creates a pattern increasingly difficult to dismiss entirely. Each vanishing tea bag, each mirror showing wrong reflections, each sequence of synchronistic numbers represents potential glimpses of the base code momentarily becoming visible through cracks in the rendered illusion. While mainstream science remains cautious about embracing simulation theory, the mathematical and empirical foundation supporting it grows stronger as our understanding of quantum mechanics and information theory deepens. Most importantly, whether we inhabit a simulation or not, quantum mechanics irrefutably demonstrates that observation plays a constitutive role in reality itself. Wave-function collapse depends on measurement. Double-slit experiments prove that watching changes outcomes, and quantum erasure experiments show that even retroactive changes to observation can alter past results. This means consciousness is not a passive receiver of external information, but an active participant in reality as construction. And if glitches occur in this process, noticing them requires a particular quality of attention that most people never develop because they're conditioned to dismiss anomalies as errors in perception rather than errors in reality. Therefore, the next time you notice something impossible, an object vanishing without trace, a reflection contradicting what stands before the mirror, or synchronicities occurring beyond statistical probability, resist the reflexive urge to rationalize it away as memory failure or coincidence. Because you might be witnessing one of those rare moments when the simulation's curtain becomes briefly transparent and reveals the computational architecture underneath. Document these experiences. Share them with others, because each observation adds another data point to humanity's collective understanding of what kind of reality we actually inhabit. The truth about existence may not come from physicists building elaborate experiments in billion-dollar laboratories, but from ordinary people paying careful attention when the familiar world momentarily betrays its own impossibility, and asking themselves honestly, what if the glitch isn't in my perception, but in reality itself?